Welcome back to the deep dive. Great to have you with us again, especially our number theory students.
Glad to be here.
We're continuing our journey through the OEIS, the Online Encyclopedia of Integer Sequences.
Yeah.
And today we're tackling A000317.
A fascinating one.
Our mission really is to unpack its recurrence relation, see how it behaves, and maybe uncover something, well, surprising about its structure.
Yeah, there's a neat connection lurking there.
So let's start right at the definition. A000031 What's the rule that generates this sequence?
Okay, so the core of it is this recurrence. an plus 1 is equal to an squared minus the product an times an1 plus an1 squared.
Right, so not just adding or multiplying by a constant. It depends on the two previous terms.
Exactly, the two previous terms.
And involves squares and products. That sounds distinctly nonlinear.
Oh, absolutely. Profoundly nonlinear. It's that quadratic relationship, the squares, the cross-product term that really drives its behavior. It's not your standard arithmetic or geometric progression.
Okay, that formula, an plus 1, an plus an1, 2, it looks sort of compact on paper.
It does.
But I imagine that nonlinearity means the numbers could, well, get big fast.
Can you give us the first few terms just to get a feel for it?
Sure. It starts off innocently enough. You have A01, A12.
Okay.
But A2 is 3. Still pretty tame.
Why 2, 3?
Then A3 jumps to 7.
Sorry, a bit of a jump.
And A4 is 37.
Okay, 7 to 37, starting to accelerate.
Exactly. And then, like you suspected, it really takes off. A5 is 11 to 59.
Wow. Okay, from 37 to over 1,000 in one step.
And it just keeps going like that. A6, the next term, is already 1,301,767.
Over 1 million. That's incredible growth from such a, well, relatively simple-looking quadratic rule.
It really highlights the power of that squaring, that nonlinear feedback. It compounds very, very quickly.
It certainly does. Which makes you wonder how you find deeper structure in something that explodes like that.
Well, that's where things get really interesting. And this seems to lead us to Emmanuel Ferrand's work. There was a paper, Deformations of the Taylor Formula, I think.
That's the one, published in the Journal of Integer Sequences back in 2007. A really key insight.
So what did Ferrand find about A00030310 that was so significant?
Ferrand discovered something quite remarkable. He found that A00000317 belongs to a special class of sequences.
Okay.
For these sequences, the associated generalized binomial coefficients turn out to be polynomials. And not just any polynomial.
Ah, okay. Polynomials with integer coefficients.
Precisely. Polynomials with integer coefficients, which is frankly quite unexpected for many recurrence relations.
Generalized binomial coefficients. That term itself is intriguing. For our listeners, maybe for me too, could you unpack that a bit? What are they, and why is it such a big deal that they are integer polynomials here?
Sure. Think of standard binomial coefficients like n choose k as building blocks for binomial expansion. These generalized ones are sort of analogous building blocks, but tied specifically to a given recurrence sequence, like our A000317.
Okay, like custom building blocks for the sequence.
Exactly. Now, usually when you calculate these for an arbitrary recurrence, you might end up with fractions or, much more complicated expressions.
Right, not necessarily neat and tidy.
Not at all. But what Ferrand showed for 00031C and a few others is that these building blocks, these generalized coefficients, simplify beautifully. They become these perfect polynomials where every coefficient is just a whole number, an integer.
Wow. So instead of messy fractions, you get this clean polynomial structure underneath.
It's like finding this hidden algebraic order, this elegance, where you might have expected complexity or, well, messiness.
So bringing it back to the students listening, what's the payoff? What does this connection mean for understanding sequences like A000317?
Well, the big thing is it creates a bridge. It connects the world of these recursive integer sequences, which can seem a bit isolated sometimes, to the very rich, very well understood world of polynomial algebra. It tells you the sequence isn't just a list of rapidly growing numbers. It carries this intrinsic polynomial signature.
Which means we can potentially use tools from algebra to analyze it.
Absolutely. Tools to understand its structure, maybe even predict properties in a way that just looking at the recurrence might not reveal. It offers a much deeper level of understanding.
That's fascinating. So a sequence defined by a fairly simple quadratic rule grows incredibly fast, yet hides this elegant polynomial structure within its generalized coefficients.
That's the beauty of it.
Okay, so we've covered the definition, seen the explosive growth, and touched on this really profound connection to polynomial algebra via Ferrand's work. An amazing journey for A000317.
It really is a nice example.
So maybe a final thought for everyone digging into number theory. As you explore sequences in the OEIS or elsewhere, perhaps keep an eye out. Consider that even simple-looking recursive definitions, especially nonlinear ones, might conceal these kinds of deep, elegant algebraic structures, like these integer polynomial coefficients. It makes you wonder what other hidden symmetries are out there, waiting in other sequences.
That's the question, isn't it? Always more to discover.